Hello and welcome to lesson 6 in unit 3. This lesson's on tension force, and this video is going to contain the first example problem. Now before we get going, a short couple little notes on tension force. Tension forces are forces that we're going to be dealing with that only do pulling. Tension forces are never going to do any pushing. There's always going to be some sort of pull action going on here. And in these tension force scenarios, generally there's going to be some sort of rope or cable, and we're going to say that the tension or the force throughout these cables is going to be uniform. Okay, even if they bend over some sort of pulley or something, we're going to ignore any sorts of friction in those pulleys, and we're going to say that they're ideal systems. Likewise, we're also going to say that the ropes or cables that we're dealing with don't have any mass. We're trying to keep things nice and clean while we learn, and then later on we can start adding in some more challenging scenarios with extra variables. Okay, well, let's jump into example number 1. So example number 1 is, it looks like a sign hanging from some sort of support system, and we have 2 strings or ropes holding this thing up, this 5 kilogram mass up, and one looks like that it is straight out to the side at a right angle. It's not labeled as a right angle, but I'm going to go out and say that that's probably a right angle. And a second cable, which is 63 degrees from the horizontal, coming out from a top support. Alright, and the question in this example asks, determine the tension in each of these strings. So number 1, we want to find force tension, and number 2, we want to find force tension. Okay, maybe we can list that on here as FT1, and maybe up here, FT2. Alright, with that I'll get rid of these little 1s and 2s. Cool. Well, couple starting points. This is a hanging sign, and we just finished the unit on gravity. A fun thing about these coming lessons is that now that we have a little bit of base knowledge, we can actually start doing some fun questions. We have a little bit of back knowledge actually within a couple topics, and it's really starting to look like physics rather than trigonometry. And that said, there's still going to be a lot of trigonometry. Anyways, let's get into this problem. I did mention that we just finished the gravity unit, and with that said, we are going to be utilizing the force of gravity here. In fact, the only force pulling this thing down is, I think, the force of gravity. Unless somebody wants to let me know on something else, but I think we just have force gravity pulling down on this thing. So we'll say this is force gravity, and we know that is equal to mass times little g. Okay, well, the tricky part now is we have force gravity going down. How do we translate that into these other 2 forces? Well, it's actually a little bit simpler than you might think. We have to break it up into x and y direction. I hope that's not too much of a surprise to you. So this tension force is only in the x direction. This tension force is at an angle. Alright, so let's split this thing up into ruler tool, into a y value. But also we can split this thing up into an x value. And we can set this thing sideways, and there we go. So here we'll have FT1x, and here we'll have FT1y. Perfect. Well, let's break this up into x and y directions now, why don't we? This sign is not moving, it's just hanging there. So in the x direction, x direction this way, F net x, I'm going to change my color up to do some math here. F net x is equal to 0. Right? This thing is not moving either direction. So we can also say that our F net y is equal to 0. That's the first of two formulas that we typically use. That's pretty handy. Now let's separate all these forces out into x and y directions. Okay, we can say that maybe blue. Let's do y first. We did x here. So F net x is equal to ft2 over on this side plus ft1x on this side. See, there's the only two things moving out in the left-right x direction. So ft2 plus ft1x. Well, what we can do is we can say that 0, because we know f net is 0, is equal to ft2 plus ft1x. And I think this is going to start coming together. We can see that negative ft2 is equal to ft1x. Okay? And if we draw our directions on here, which I usually have been pretty good at starting the video with, but I did not for this one, we have this can be a positive direction, up can be a positive, left we can say is negative, down we can say is negative. Okay, so really this negative t2 is saying that a negative negative, the magnitude of ft2 is going to be equal to the magnitude of ft1x, just in opposite directions. That's what that is saying. If we do this in the y direction, well, it's essentially going to give us the same thing. It's going to give us force of gravity is equal in magnitude to ft1y. Okay. I'll write that out. Might as well. Give us a nice dark green here. And for f net y, I'll do it down here. F net y is equal to ft1y plus fg. And so 0 is equal to ft1y plus fg. So negative fg is equal to ft1y. Right? Force of gravity has same magnitude as ft1y. They're just in different directions. That's all that expression is saying. Okay, with that said, let's find ft1y and ft1x. Because if we find ft1y, well, we will be finding ft1y using force of gravity. Then using that, we can use, what's this going to be, sine rule to find ft1x. No, sorry, tan rule to find ft1x, sine rule to find ft1. So I hope I wrote small enough here. It's going to be a little tight for space maybe. Okay, so we now know that in the y direction, ft1y is equal to force of gravity. So let's solve force of gravity. What color do we do this one in? Red maybe. So let's say ft1y is equal to force of gravity. So ft1y. Actually, no, I don't want to start that way. That's ugly. Let's just find force of gravity. Force of gravity is equal to mass times gravity. So 5 kilos times 9.81 meters per second squared. Okay, so we plug that into our calculator and we end up getting force of gravity equals 49 49.05 newtons. And that is down. Okay. So when we plug that into some sort of Fnet formula, right, we're going to get, or you'd be using a negative value. In fact, if we use that right here, we would end up with a negative value. Okay, so Ft1y is equal to negative Fg, and this is where it gets a little bit weird. I kind of wish I hadn't done these two steps to demonstrate. I probably would have skipped this, and then just saved it so I could substitute in negative Fg right here. But I think most of you are getting to a point where your algebra is strong enough that you see what's happening here. Because now we have Ft1y is equal to negative, right? The negative in the formula minus the, or times the negative 49.05 newtons. So Ft1y is equal to 49.05 newtons. Ah. Okay, good start. I am going to have to conserve my space a lot better though. Alright, next part is, now that we have this Ft1y is 49.05 newtons, we can either solve Ft1 or Ft2. Ft2 in the x direction is equal to this Ft1x in the x direction. Let's do Ft1 first, because we can just do it directly. So let's pop into magenta again and brighten it up. Okay, so Ft1. How are we going to go about solving that? Well, I already mentioned it. I just want to make sure I don't mess it up here. And I'm going to say that sine of 63 degrees, what's that? 63 degrees is equal to opposite over hypotenuse. Right? Yes, opposite over hypotenuse. So that's equal to 49.05 newtons. Right? This is our opposite side to our angle. And we're solving this hypotenuse length over Ft1. So we are going to end up having a situation where we have rearranging this, Ft1 is equal to 49.05 newtons over sine of 63 degrees. That, to me, gives us a value of 55.05 newtons. All right. That is half of our answer, right? We just solved Ft1. We don't need any directions or anything on this. It's just simply asking us for the magnitude. The direction is already given, right? This is 63 degrees from this horizontal value. So that's nice. We don't need any direction on that. All right. Second force value. Well, we have now solved this as 55.05 newtons. Let's solve Ft2. Ft2, which we have down here, negative Ft2 is equal to Ft1x, right here. So let's find Ft1x, and then we have Ft2. Going over to blue. I haven't used blue for a while. Actually, no, I haven't used red at all. Let's use red. Okay. So Ft1 1x. No, I'm going to use a tan rule here. So let's say the tan, I can write it all out. Yeah, tan of 63 degrees is equal to adjacent over hypotenuse. So ft1x over adjacent over opposite, 49.05. Okay. And we do some rearranging. So ft1x is, I'm just checking my work here to make sure I don't make any mistakes in this. Opposite over adjacent, you see I have already made a mistake. Tangent is opposite over adjacent. So this is going to be 49.05 newtons over ft1x. That's better. So now ft1x is equal to 49.05 newtons over tan of 63 degrees. Perfect. Leaving us with ft1x equal to, what do I get here? 24.99 newtons. So 24.99 newtons. I didn't actually check my sigdigs for my ft1 value here. So let's take this final answer box off and do some correct sigdigs. ft1x was equal to 24.99 newtons, which also means that ft2 here is equal to ft1x. So, which is equal to ft2, which is equal to 25. There's only two sigdigs in this question. So it's equal to 25 newtons. That one all box. Okay, and going back up to ft1. Alright, ft1 right here is just 55.05 newtons. So let's make it pretty, back to magenta, and say, whoops, that's not the right tool. This is 55 newtons, ft1. And there we have it. The two forces based on one force of gravity and two forces of tension.